Have you ever wondered that how charge behaves in electric field? So let's say here we have a positive charge and it has an electric field around itself, and this charge will denote it as Q. And let's take another charge which we called as test charge, right? So this is kind of test charge, we are using it, right? So this is test charge and we actually denoted the test charge with Q naught, right? So now we will consider that what happens to this test charge when it goes in the electric field of this big positive charge. So basically we are studying the interaction of electric fields and field forces. So now this test charge will enter into the electric field of this big charge Q. So this charge Q naught is now inside of this electric field. Now we know that electric field due to positive charge is always goes outwards from the charge. So this is basically here and like this. So this is the direction of electric field that possesses the charge, right? So this positive charge has an emerging electric field, and this is what we call as field. This is what we call as field, right? So this is electric field of this positive charge. Now since the test charge is positive, so basically test charge will repelled by this big charge. Why? Because this is positive and this positive test charge is also positive. So we know that the two like charges always repel each other, so there's a force of repulsion. There's a force of repulsion here that will act on this test charge. So this is kind of force of repulsion, right? Now this force can be given in the form of Coulomb's law. Now we know that how Coulomb's law can be written. So this is basically let me change the size of this color. Now Coulomb's law, according to the Coulomb's law, so basically Coulomb's law, the force acting between these two charges is equal to obviously 1 by 4 pi epsilon naught, and this is q naught over r square. Now what is r square? It is the actual distance between these two charges. So basically it is a positive charge, and from here to from here to here. So this is what positive charges look like. So from here to here, this is r, right? Now force of attraction or maybe force of repulsion will act in the form of Coulomb's law. Now we are going to study the electric field due to a point charge. So basically how this force acts on this positive test charge, it is due to the electric field. Now because let me take a rough work. So this is positive charge and this has the Q charge, and now from here to here there is another test charge that we're using here, Q naught, and the distance between these two charges is r, obviously. So basically this positive charge has an electric field at this point. So electric field at a distance r, we will denote it as E vector, right? You understand? So electric field actually apply force on this test charge. So this electric field, this test charge will experience the electric field due to this positive charge. Now this electric field applies force on this test charge. Do you get this? So there is a note, and in this note we will write that electric field applies force on charge, right? So this is our note, or we can say this is our remark, that the electric field applies force on charge wherever there is an electric field, and if we put a charge on that point where some electric field is present, then that electric field will apply a kind of force which is called the electric force given by the Coulomb's law. Now this force experienced by this test charge is called electric field. So the formula for electric field is just given by that the electric field is equal to the force experienced over per unit test charge, or maybe charge, whatever the charge would be. So now we know that which charge is experiencing the force. Test charge is experiencing the force and it is going outwards due to the repulsion force. So we can say that the electric field at the point P, let's say this point can be taken as P. So this is point P. So electric field at point P due to the Q charge can be written in the form of force over charge. Right? So do you get this? That the test charge, or maybe we can write it as Q naught. This is called the test charge. Right? So basically, what electric field would be is just electric field at point P. We can write the expression for the Coulomb's law, which is the expression for the force as well, which is 1 by 4 pi epsilon naught Q naught over R square. And now we are dividing this force with the Q naught charge. So we can write it as 1 over Q naught. Now this force is divided by this Q naught charge, and now the Q naught will cancel out each other, and the expression for electric field will remain 1 by 4 pi epsilon naught Q over R square. Now this is very, very fundamental formula for the electric field. Now for this time we are just seeing only magnitude form of the electric field, right? So we are not taking it as as a vector form. So basically we are erasing this vector sign, because this is just a magnitude, the magnitude of electric field, right? So now the conclusion is this positive charge, the Q1, has an electric field at a point which is r distance farther from the charge, and this is the point at P. Now at this point the electric field is this one, kq over r square. Now we know that the k is the Coulomb's constant, which is equal to 1 over 4 pi epsilon naught. So this is the expression for the electric field. Now we can write this electric field in the form of vector form. So in vector form, so in vector form we can also write it as the electric field is equal to, so electric field, now we can take it as a vector, which is equal to 1 over 4 pi epsilon naught Q over R square. Now since we are taking the vector form, so we must have to multiply it by the unit vector of distance. So what unit vector of distance is? This would be r cap, right? So this is our final formula for the electric field in a vector form. Now we can also write it in the form of just like it, the electric field vector would be equal to 1 over 4 pi epsilon naught Q over, now we can multiply it by r vector as well. So if we multiply it by r vector, then we have to divide it with the r vector. So this is basically r vector magnitude and Q, because r square, and if we multiply r by r, so we can conclude that r square into r would be r vector cube. So basically its magnitude, and r into r cap would be equal to r vector. So this is also a magnitude form of electric field, right? So now you get this. So now we can conclude that the electric field at any point due to any charge, it may be positive or it may be negative, that this is just directly proportional to the charge and inversely proportional to the square of the distance between them. Now here is a main point, so important point, you can note it down. So important point is, you can say it remark as well, remark that the electric field here is directly proportional to the charge, because if charge increases, the amount of electric field at the point P also increases. So this is the first remark that we in the examination it is basically and frequently asked. And this electric field is also inversely proportional to the r square. So this is directly proportional and this is the inversely proportional, right? Now let's talk about the SI units as well. So SI unit of electric field, SI unit of electric field. Now we have always seen that any SI unit of any unit can be found with their formula. So the formula for the electric field is just force over charge. Now in the vector form, this is electric field vector is equal to force over charge. Now the SI unit would be the SI unit of force, which is actually Newton, and the SI unit of charge, which is actually Coulomb. So the SI unit of electric field would be basically Newton over Coulomb. So basically we can write this Newton over Coulomb, Newton Coulomb to the power minus 1. Now let's take an example of how electric field works. So here we have a question here. So if you have a charge, let's say, and this charge has a magnitude of, let's say, 4 microcoulomb, right? Let me change the size of this. So this is basically 4 microcoulomb. One second, 4 microcoulomb, and at a distance of 2 meter or maybe 2 centimeter, calculate the electric field at this point. Now what would be the electric field at a point P? So we can easily calculate with the formula. Now the electric field, now what is given here? So if we take a solution of this, charge is given. So basically the Q charge is 4 microcoulomb. We can write it micro as 10 to the power minus 6 coulomb, and the distance R is equal to 2 centimeter. We can also write it with 2 into 10 to the power minus 2 meter. 1 centimeter is equal to 100 centimeter would be equal to 1 meter. So basically 1 centimeter is equal to 10 to the power minus 2 meter. Now we want to calculate the electric field at a point P. So electric field at point P would be equal to EP, obviously. Now the EP has the formula that the 1 by 4 pi epsilon naught Q over R square. Now we know that what is the value of the Coulomb's constant. You must have remembered that the 1 by 4 pi epsilon naught has a unique value, which is equal to 10 to the power minus 9 into 10 to the power minus 9, and we can write the SI unit as well. So this is Newton meter square over Coulomb square, right? Now the charge has the value of 4 multiplied by 10 to the power minus 6 Coulomb, and the radius, which is actually the distance, 2 centimeter, has the value 2 over 10 to the power minus 2 meter, and we have to do the square of the radius, square of the distance. Now we can calculate it. So this is EP would be equal to 9 over 10 to the power 9 multiplied by 4 into 10 to the power minus 6. Now this would be 4, and this would be 2 into 2 minus 4, and this is Coulomb, and this is meter square. So now let's sort out the SI unit. So the SI unit is Coulomb over meter square here, and the Newton meter square per Coulomb square here. So Coulomb over Coulomb would be cancelled out, meter square would be cancelled out, only Newton per Coulomb would remain. Now let's sort out the magnitude. So 4 and 4 would be cancelled out by 1. Now this would be 9 into 10 to the power 9 minus 6 and minus over plus 4, and this would be Newton over Coulomb. So now we can simplify it by 9 4 13, and 30 minus 6 would be equal to 7, right? So 9 into 10 to the power 7 Newton over Coulomb. Now this is the electric field at point P. Now if you have to calculate the direction of electric field at a point P, so you can calculate it by knowing the sign of a charge, like the nature of a charge. So now we know that the Q charge is basically positive. So this is positive 4 microcoulomb. So it has an emerging electric field at a point P, which is basically radially outwards from the charge. So this is charge and this is point P. So radially outward means like this. So the electric field at point P would be like in this direction, EP, and it has a magnitude of 9 into 10 to the power 7 Newton per Coulomb. Do you get this? So I hope you get this, and let's meet